Today we are going to discuss numerical problems based on electric flux and Gauss law. So in first problem, find the total flux due to charge Q associated with the given hemispherical surface. Given hemispherical surface. Here the first case is a hemispherical surface, hemispherical, and here the charge. So here the electric field, total electric flux. So here the total electric flux is equal to Q enclosed by epsilon naught. This charge sharing another hemispherical surface. So this charge sharing this hemispherical and this hemispherical. Total Q or Q divided by 2 epsilon naught. Here the, according to Gauss law, here the flux is equal to Q enclosed by epsilon naught. Enclosed charge here 0. That's why here the 0. Here the inside the charge. Here the flux, in this case flux is equal to Q divided by epsilon naught. Q enclosed charge here Q. Here enclosed charge sharing charge. So here the flux is equal to, here the out of the charge out of the enclosed. So here enclosed charge is equal to 0. That's why this one also 0. Here also enclosed charge is equal to 0. That's why here the total flux must be equal to 0. So now another models flux calculation using Gauss law. So first one, this one is a uniformly cylinder. Here the electric field passing through the cylinder, and here the surface area. Here also surface area, here also surface perpendicular to this plane. So here the electric field into the cylinder. In that case, our electric field into the means flux into the. Flux into this case nothing but already we discussed minus electric field into area. So area is nothing but pi r square. This radius I would like to consider capital R. So pi r square into electric field. So into electric field. Similarly out. So electric field coming out direction only positive. Flux positive already we discussed. Pi square electric field. Total electric field. Total nothing but inside plus outside nothing but inside minus pi r square E, outside plus pi r square E. Get cancel, outside 0. Total, not outside 0. Total flux 0. Total flux 0. Now second one. Let us consider this one is a hemisphere. This sphere radius capital R, and here the electric field into this hemisphere and coming out of the hemisphere. Here in the electric field or electric lines are passing through this area is nothing but flux. That flux enter to the hemisphere and the flux coming out of the hemisphere into the hemisphere, in that case minus pi r square electric field, and into minus, already we discussed, already I said that point also, plus pi r square electric field, So total nothing but inside plus outside nothing but total 0. So here the one cube, here the electric flux enter to this one, or electric flux enter to this cube inside the electric field. So here area into electric field. Area nothing but each side A, nothing but area nothing but A square. So minus A square into electric field. So out, coming out of the cube, plus A square into electric field. Total 0. So let us consider here one more model. So here the one cube, here the this charge placed at one corner. So if q placed as shown in figure, seven more identical cubes are required. It's enclosed. Required to enclose. So that's why here this charge distribute or contribute to the another seven cubes. So that's why electric flux also sharing or contribute to another remaining 7 cubes also. So remaining 7 plus this one is a 1, 8, total 8. This charge contribute to total 8 cubes. That's why enclosed charge q by 8 into epsilon naught. Similarly here also, here q charge placed at showing the diagram, placed in this place. So here three identical cubes are required to enclosed. So in that way, flux q by 4, 3 plus this one, total 4 epsilon naught. So here the one more example, uniform electric field. Here hemisphere moving, placed it like this, and here place it to see the diagram. You may observe the diagram. Here the inside the into the flux is nothing but this one look like a area, nothing but 1 minus 1 by 2 pi r square into E plus 1 by 2 pi r square into E, and here total 0. Now another model as shown in figure, a closed surface intersect a spherical conductor if a negative charge is placed at point P. What is the nature of the electric flux coming out of the closed surface? So here point charge Q, individual charge on conductor, net charge enclosed by closed surface is negative. This negative charge. So flux also negative. So net enclosed charge by closed surface is negative. So flux is also negative. This is the answer to the question. Another model, consider electric field is equal to 3 into 10 to the power of 3 I cap Newton per coulomb. Then the flux through the sphere of 10 centimeter side, if the normal of its plane makes angle 60 with the x-axis. So what they are asking here, flux coming out means positive flux, always positive flux. My dear students, you may remember, out of the surface coming out, that flux always positive, into the surface or into the body, in that case flux negative. So here the E S cos theta, general formula. E is nothing but 3 into 10 to the power of 3. S nothing but 10 into 10 into 10 to the power of minus 4 into cos 60. Cos 60 nothing but 1 by 3. So this one get cancelled. So 30 into cos 60 1 by 2. So 15 15 Newton meter square per coulomb. How much flux amma? Total flux 15 Newton meter square per coulomb.